In this video, I'm going to walk you through the unit storyline for Unit P1 from OpenSciEd. Now you can see in the window below that I have provided a table of big ideas that are developed throughout the unit. It's really important to know when things are being developed so you don't introduce ideas a little too early. It also shows some key terms and when they're developed, and a lot of teachers like to use these big ideas to help develop maybe some formative assessments or checks for understanding, and possibly add a few grades to the gradebook. Okay, I'm going to walk you through the unit storyline. This one comes from your Google Drive. If you downloaded the unit, it's in the unit overview document. And I'm going to walk you through a couple things. First thing I want to point out are these icons. And these icons up here in the top right corner appear here as well. And they share which routine of the storyline routines that you're in for this lesson. So you can see the first lesson is all about the anchoring phenomenon routine. Every single unit will include the anchoring phenomenon routine in the first lesson. The second lesson has an investigation as well as some reading. So anyways, these icons, there's a key right here. You can also see the amount of days that it takes to do this lesson. I will say if this is your first time implementing this unit, that it will take longer than the suggested duration. That's just normal as you get to know the unit. Okay, so let's begin. This unit is all about the unit question, how can we design more reliable systems to meet our community's energy needs? Now, the anchoring phenomenon in this unit is all about that blackout that was experienced in Texas when there was a really cold winter storm and much of Texas lost power. So it's very curious why certain areas of Texas lost power and certain areas didn't. So we're going to read some articles, jigsaw them with students to kind of learn a little bit more about the blackout, as well as looking at a blackout map to see where the blackouts happened and come up with some ideas and some questions about what has happened here. Students then make an initial model to try and explain, and there's some prompts in there to try to explain where the energy came from, how it gets to buildings, and how did this blackout occur. And then we have an initial consensus model that we make together as a class. You can see an example of it right here. The teacher guide will walk you through how to divide this into 3 sections. And so as students give you ideas, you are definitely recording source of energy in one section, transport of energy in another section, and then the destination of that energy in the third section. And so we're going to actually ask questions that will align to these 3 categories. I have a few more categories that I will provide in lesson 1 video, but that's basically it. We then ask questions and we are curious about not only why did this happen, but how can we build a more reliable system? So this is actually an engineering design unit, and we will be designing a community solution for our own communities using a computational model called the energy grid calculator. Okay, let's move into lesson 2. So in lesson 2, we're going to answer the question, what structures in the system enable energy transfer from one source to multiple devices, buildings, and neighborhoods? And we use this really cool model of a surge protector as the energy source. And we are going to, it actually is not plugged in, it's connected to a battery as the energy source. The plug is removed. And then we have different lights, and we make an electric city, and we show how one energy source can light up multiple buildings and multiple places in a community. Of course, first we have to really develop the idea of an electric circuit, a complete circuit, a broken circuit, and we even get into short circuits. And we have models to kind of show how this happens. One is a poster model or a paper model that you develop with students, and the other one is this physical model using the surge protectors. In lesson 3, we're answering the question, could the blackouts in Texas have been caused by a broken or short-circuited circuit? So in lesson 2, we start to develop those terms, but now we're wondering, could that have been the problem in Texas? And so we read an article about an energy crisis and about some broken power lines, and we actually model several different scenarios. There's a lot of energy transfer modeling happening here. So here's scenario A. This would be normal operations. You can see the electric electricity is going from the power plant to the power lines to a substation, which you will develop with students, and then to 3 different houses or buildings. In another scenario, a tree falls, and so it breaks a couple lines, and you can see that all of the energy, instead of being distributed to the 3 places, is being directed to the one place where the tree is, because we have a short circuit. It's the path of least resistance, and that's where all the electricity will flow. And so the broken line is actually here where the tree is, and it's going into the tree. So we're going to model 5 different scenarios about how energy will transfer if we have different, like a short circuit, a broken circuit, those types of scenarios. In lesson 4, we're going to answer the question, what makes an energy source reliable? So we're going to use these different energy source cards, and we're going to learn about things like wind power, solar power, biomass, coal, natural gas, all of the different types of energy sources. And we're going to also figure out which sources were used in Texas. We're also introduced to a decision matrix, an engineering decision matrix, and we start to develop some criteria that would help us evaluate energy sources. Now, remember, this is an engineering unit, so we're not only developing the science ideas around electricity, but also the engineering ideas around how to solve a problem. In lesson 5, we are going to compare 2 energy transfer models. We actually developed them. One is for a wind power plant, a wind turbine power plant. The other one's for a natural gas power plant. And we show the energy transfer models. We also, are using some of these rules like the system boundary, and we're talking about maybe what energy is going to the surroundings outside of our system boundary. But what we realize is that both power plants have a generator. And so this asks some questions or creates some curiosity about, well, what is this generator doing? How is it taking wind power or natural gas power and turning it into electricity? And so we build this generator model. It looks like this. We have several different generators that we build, different amounts of looping copper wire around that cardboard tube. And so we kind of, dissect the generator and figure out what is happening in that generator to cause the electricity to be transferred. And so we're really developing ideas around magnetic fields and electric fields, and how when matter or motion happens through contact, energy can be transferred, but it can also happen across a distance, so across a space. And so the magnetic field can actually push, well, we're not getting into electrons yet, but can push energy into wires. And so that's going to lead us to what's going on in the wires. And that leads us to lesson 6. We read an article about how copper, the outer electrons of copper are held pretty weakly to the nucleus. And students should have this from chemistry. If you have not really gotten into protons, electrons, and neutrons, definitely there's going to be a gap needing to be filled here. But we've got some electrons that are loosely held on by the nucleus, and they can easily be pushed off, and those electrons push each other, which cause an electric current. And so we're then realizing that the electricity is coming from these magnetic fields pushing the electrons. And this also, when this happens, can create some heat energy, and that heat energy is actually lost to the surroundings. So we consider kind of like what factors are going to lose energy to the surroundings. In lesson 6, we also have a transfer task at the end of the lesson. So that means we're going to take all the science ideas that have been developed so far, and we're going to apply them into a new scenario. We transfer them to a new context. So we will be using the scenario of motors and how electrical fields and magnetic fields create a motor. And so that will happen at the end of lesson 6. In lesson 7, we're starting to go back to the problem in Texas, and we're going to answer what could have caused the disparities we saw in the blackouts in Texas. We remember those maps where some areas the lights were left on and some areas the lights were turned off during the blackout. And we use a model showing that supply was actually the issue. There wasn't enough supply to meet the demand. So we start getting into this idea of supply and demand and how the demand was not being met. We make some models and we figure out that when there's not enough energy supplied, that the buildings will not all turn on, or if we go back to that electric city, that all three destinations will not turn the lights on. But if you cut off the pathway to two of the buildings, one of the buildings will have the lights on. So we need to move all of that electricity to one destination to keep the lights on there. And so we're realizing, why were these decisions made in Texas to have some buildings left with their lights on and some buildings not? And we look at some discrepancies and inequities in the data. And we can't find one single factor that led to these decisions. In lesson 8, we go a little deeper into looking into the disparities between and you can see here's a satellite image of the map of Texas, and you can see where the lights were on and the amount of percentage of the population where the lights were out. And really at the end of this, we look at some fictionalized families and impacts, but really at the end of this, what we're realizing is that there were some essential buildings in the areas where the lights were left on. That would be like hospitals, things where we definitely couldn't have the power turned off. And that led to the decisions that were made by the decision makers. So now in lesson set 2, we start thinking more about those decisions that decision makers make. And so we think about the design of the system, and could we have created a system that stored energy so that when there wasn't enough supply, there was excess that we could have brought into the system. And we read an article on batteries, and we realize that we can calculate the amount of batteries needed to have filled that gap in Texas, because we know the energy demand that was being asked of the power grid. So if we know that amount of energy, we can calculate the amount of batteries, which means we can also calculate the cost. So this starts bringing in decisions based on cost. So batteries would be a great reliable system, but they're expensive. And so now we're thinking that there might be other costs and benefits that decision makers also put into their decision-making process. In lesson 10, we start to think about trade-offs. And so who is making the decisions? What are the interested parties? Who has influence from those interested parties? And so we're really developing more about the criteria and the constraints. And we go back to that decision matrix. And this is when the engineering challenge is assigned to students, where they're going to create a plan for an energy grid system for their own community using ideas of their criteria and constraints. They're going to pick what they think are the most important criteria and constraints to basically help them make their decisions. And then they're going to design a power grid. In lesson 11, we actually test those power grids, not so much by making a model of them, but by using what's called the energy grid calculator. It actually has all the information for the communities around the United States. And so they put their decisions into this energy grid calculator, and then they can kind of measure the success of the solution. They also share their solutions, get feedback, some more of the processes of engineers and the engineering design process. And then there is a final assessment task in lesson 11. And this one, again, takes all of their science ideas and engineering ideas and then applies it into a new context. And this time it's called the solar sand. It's about a solar power plant that uses sand and mirrors. That's what's called, sand and mirrors. So that's it. A lot of energy transfer development and electricity and electric grid development here, but also a lot of engineering ideas. I hope that helps.